finding where a function increases or decreases by using derivatives. Once you kind of get a good grasp on derivatives, you'll notice that, it's not super hard to take a derivative and then being able to understand what the derivative is, which is nothing else but a function, which just tells you what the slope of that function is at every single point, okay? So where it's defined. Now, if it is the slope, then that means it's kind of the rate of change. And if you are interested in finding a function and where it is increasing and decreasing, then derivatives actually become super useful if you want to be able to see that. So let me explain it on a very simple example, and then we'll take a little bit harder example and an even harder example. And of course, you can extrapolate to almost any function. The only problem is, of course, if you make the functions way too complicated, finding derivatives on its own is going to be a headache. Okay, so for functions that are, for example, polynomials, some quotient functions, okay, and then some other functions which are not as super complicated, okay, this process is going to work very, very well. And I guess as a student, when you're taking calculus for the first time, especially in high school or maybe early on in post-secondary, then these skills are kind of useful because you can't always use tools, which I, for example, use decimals a lot to show you through videos. Okay, so you have to know and get comfortable with doing these derivatives and then finding where functions increase and decrease. So let's take our simple quadratic function, which we completely understand. So let's say if I would give you fx is equal to x squared. So we know exactly how this function looks like. So let me just sketch it. All right, so here we go. So that's our parabola. So we know that it's centered basically at 0 over here. And now, what do we mean by this increases and decrease? So first of all, when we're saying a function is increasing and decreasing, what we mean is that we are coming, okay, so from the left and we're going to the right. All right, so that's what we mean. Because of course, if you're going from the right to the left, then it might mean something else completely, okay? So we're always thinking going from negative to a positive, right? So from something smaller to something bigger. So we're going from left to right. So as we go along this function, we can clearly see that this function along here is decreasing, right? So it's decreasing, 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 until eventually, it'll hit over here, which is 0, and then it starts to increase, right? And then it starts to increase and it's going up and up and up. Now, for a quadratic as simple as this, not very difficult. And actually for most quadratics, if you've done anything with regards to functions, okay, of the courses from grade 11 or even the advanced functions in grade 12, then sketching quadratics is not a big deal, right? But knowing the derivative itself does help us when we want to apply it to something that we can't really visualize as easily. So for instance, in here, if I wanted to find increases and decreases, then I know that my function, basically what happens is that from negative infinity, all right, and then going forward, so as x, okay, goes in this direction, and it's less than 0, so we know that the function is decreasing, right? So we can see that. Now, if I would take the derivative here of f at x, so here what I would get is that my derivative is equal to just simply 2x, which is just nothing else but a line with a slope of 2. So what I would have if I plotted it out here, so it would kind of look probably something like that, right? So this is going off in this direction. We're assuming that the slope is 2. And here we can see that once again, that our derivative right here at x is equal to 0, the derivative is 0 itself. So that means that our slope would have been flat, right? And that's nothing new to us. We can see that on the parabola, that it would have been a flat tangent if we wanted to attach it at that point. Now, for the derivative, we can see here that as long as it's on the negative side, and then of course this keeps going, we can see that indeed it matches up, and the derivative when it's negative is telling us that the function is decreasing. So when we have a negative slope, okay, then we know that the function is decreasing. And if we have a positive slope, so let's say, if I wanted to go off on this side, so if I would have a positive slope, which indeed is the case for positive x, what I would have here, this would have been a positive slope, then my function is increasing. And again, this is from going from left to right. And very often what's useful here is if you wanted to find out without plotting anything, what you can do is you can take the derivative, so in this case would have been 2x, and then you can set it to 0 and find out where that happens. So now if I solve this, of course, this happens at x is equal to 0, which is, that point right there. And that just simply tells you where the slope or the tangent line is just 0, right? With regards to the original function, because that's what derivatives tell us. And now what we like to do is we like to kind of create a little table for ourselves and say that, okay, well, what we do know is, so let me just kind of shift this over, I'll duplicate this. So I'll have, so within here, duplicate that, okay, shift it over. So what I have here is at x is equal to 0, we know that the actual slope is 0, right? So we know, let's call the slope m, okay? So the slope is 0. Now for x, which is going to be less than 0, I know that the slope is negative. Now I can find that out because, so notice 2x, so this is my derivative. What we like to do is just pick a test point, which is less than 0. It doesn't matter what it is, and we'll do that in other functions as well. So we can take a test point, take the easiest one, let's say -1. You substitute -1 into your derivative, so it's going to be 2 times -1, which is -2, and that just tells you, okay, that the slope is going to be negative. And then for x, which is greater than 0, right here, okay, so for that, we can see that the slope is actually positive. Again, you can take a test point, set x is equal to 1, substitute it back in, so 2 times 1 is going to be 2, and it's positive. So this just simply tells us what the derivative is. And what that means for the actual function, so this function is decreasing on this interval. It is 0, okay, so that means it's flat right here. And then it is increasing for this interval. And it is all dependent on what the slope actually is. Now again, we can clearly see that from the function. But we want to be able to use this skill when the functions are a little bit more complicated. All right, so let us take a look at a more complicated example and then see, are my functions increasing or decreasing and on which intervals? Here's another example that we have. So this one is obviously a little bit tougher. Let's try to go through the steps that you would take in order to be able to find out where a function is increasing and then where a function is decreasing. And then I'll pull up decimals to try it visually so that you can see, how it relates back to the actual function so that you have some intuition and a visual for yourself. So the first thing that we do is we take the derivative. So we're going to take the derivative, we're going to find that. Now, this is, a cubic function, so it's well defined everywhere, so that's great. And the derivative would be just 3x squared plus 8x minus x. Once we have the derivative, our first goal is to find out where the actual rate of change is 0. So we would simply take our derivative, so it's a function right here, and then we would set it to 0. So now you're going to have to find your skills to try to go back. I mean, this is a quadratic, so it's not that bad. So in terms of this, I'll just use the quadratic formula, and I'll do it in fast-forward fashion. If you forgot about the quadratic formula, I'll put up a link up above there for you, okay, on how to use it. All right, so here's the answer. So this is if you want it to be exact. And then here is the two roots of the answer. So one is positive and then one is negative. Now, once we have this, then what we want to be able to do is, you can create a table for yourself. So I'm going to create a table, but what I'm doing is the following. So this is what the table that I'm creating. So let's say this is going to be negative 2.786, so on. I rounded that, by the way. And then here on the right of it is 0.1196, and etc. And now what we know is that at these 2 points, we know that the slope is 0. So the function itself is flat. Now what we want to do is we want to be able to find, all right, so to the left of that, and you can put and pick any test point that you like. So, let's say I'll pick a test point of -3. And I want to now know what happens if I substitute -3 back into my function right here, so my derivative, to see what it will give me. Okay, so if I substitute it back in, so -3, it's going to be 9, 27, minus 24, minus 1. So I guess this is going to be positive, right? So it's positive 2. So on this side, the derivative is positive. So what does that tell me? If the derivative is positive, that means that the function must be increasing. All right, so here the function is increasing, right? And you can create a table, or, I like to do it like this. Now, the second thing, so I'm going to just change color. So now I want to find out what happens here in this interval right here to this function. So it looks like it's increasing, then it's going to be flat. So it's going to go like this, it's going to be flat at that -2.78, etc. And then most likely my guess is that it's going to go down, right? So it's going to start coming down like so. Okay, so let's take a look if that is the case. Now a nice test point here, I guess, would be 0. So I know 0 is probably somewhere all the way over here, but it's much nicer to just plug that in, because if I plug in 0 into here, so that's going to be just -1. So indeed, so this is negative. The derivative is here, so the function is decreasing on this interval. And then my last interval, which is going to be to the right of it, now this will now simply tell me, okay, what is happening there? And again, so I guess it's going like this, it's coming down, it's flat, and then it's kind of taking off. I know that also because it's a cubic, right? So I understand how a cubic works on the extremes, okay, on the left and the right, because it behaves like a cubic, which is, so this is the cubic parent function, which basically kind of looks like that. So on the extremes, it should look like this. So I should see that if I substitute now something in here, so let's pick 1, all right, let's pick the number 1. On that interval, what are we going to get? So substituting 1, so that's 3 plus 8, okay, so indeed, so that would be 11 minus 1, so that's 10, so this would be positive. So the derivative here is positive, so the function is indeed increasing. So although, the details here, so how it looks like, is going to be, something like this. Now, I don't know where exactly it crosses through. I can still find that out. I'm not sketching the whole function, but most likely, this function kind of looks like this. So it's increasing, hits a flat at that -2.786, starts to decrease, and then starts to increase like this, where this is the second one. So this, where it's flat over here and flat over here, that's this point. And then that's this point, and that's kind of the function. That's my guess what it would be. I could sketch it much nicer. That's in future videos to come. Here we're just interested in, is the function increasing or decreasing? Let me take out Desmos. I'll try to do that. And let's plug in this function. So this was g x equals, I guess, x cubed plus 4x squared minus x minus 2. So there you go. I mean, I kind of guessed. I wasn't sure if it's where it crosses the x-axis, right? I can certainly find those places where those places would be. But indeed, so notice here it's flat, which is the -2.786, and then over here, okay, this is the 0.1196, I guess, which is rounded by decimals to 0.12, and those are the values. So you can clearly see that that is indeed the function itself. Now, if I took the derivative, which you can just do it by taking a prime on decimals, like so, okay, so within here, notice that's the derivative right here. So notice that to the left of negative 2.786, the derivative is positive, right? This is just a quadratic. Then it's negative all the way throughout until it hits, you know, this point, which is the point of 0.1196. So below the zero, it's negative, and above the zero, it's obviously positive. And it relates back to the function itself. So that's pretty neat. Okay, so that's what we would have over there. All right, let's do one more example. Now, the examples when, you know, you have a quadratic, when you have a, you know, cubic, you know, even if it's a little bit higher order, they're not as bad because they're pretty well behaved. Now in here we have, you know, a quotient, so a function, so we have a numerator and denominator, so getting the derivatives is going to be a little bit more challenging, but we can certainly do it. Finding where things are zero, it's not going to be as easy here, or well, we'll see. And then we do have to be careful. So the first thing that I'm going to be careful here is that this function, so this, you know, we cannot have x is equal to -2 because this function is going to blow up on us there, right? So it looks like it's discontinuous at that particular point. It looks like it's an infinite discontinuity here. If you try the limit as x is approaching to -2, you'll see that it is discontinuous there, and it's an infinite discontinuity. So, you know, we won't have a derivative there. All right, how about everywhere else? So everywhere else, if I take the derivative in here, okay, so since this is a quotient, I'm just going to use the quotient rule for this. So it's going to be 2x times x plus 2 minus, I guess, well, the derivative of the denominator is just 1. So 1 times x squared minus 1, and this is going to be all over the denominator x plus 2 squared. Now, if you forgot about the quotient rule, I'll put it up above there so that you can go ahead and practice it again. And now notice that this is our derivative. I'm going to simplify this a little bit. So 2x squared plus 4x minus x squared plus 1. That's in the numerator. The denominator still stays as is. Okay, let me collect like terms, which is this one. So, okay, so this won't be as bad. 4x plus 1. I think that's the case, all right. And then divided by x plus 2 squared. So that is the derivative. So now again, so step 1, you want to set this derivative equal to 0, right? So we want to take this and we want to set it to 0. We want to see where the function is flat. Okay, so obviously it will not work for this, right? Which again is our restriction right here. So our derivative doesn't exist there, which makes sense because the function is discontinuous at -2. So in order to solve this, you know, I can multiply both by x plus 2 squared, so that's going to get rid of that. So really what I'm solving for is this, x squared plus 4x plus 1 equals to 0. So again, another quadratic. I'm not going to waste my time. I'll just use the quadratic formula. All right, so I'll be right back. All right, so we're back. All right, so these are the 2 points. So we know we have, you know, some problems here. And this is how we would tackle this. So now we do have to be careful. So what do we have? We have this, and we cannot forget this one. All right, so when you are setting, if you do find that the function is discontinuous somewhere, or the derivative gives you a problem, okay, at a particular point where it doesn't exist, so you do have to also work that. So if this is my number line, so the way that I would proceed is I would do this. So -3.7, whatever this is. Now, by the way, here's the exact answer, okay, where the slope is 0. Then I guess I would have -2. then I would have negative 0.2679. So I'm going to have a lot. So within here, I know that right here and right here, the slope is 0, right? So the slope is 0 here, the slope is 0 here. Here at negative 2, it does not exist, All right, so it's an infinite continuity. So it's going to blow up somehow, right? So we'll see in just a moment. And now we want to be able to see these intervals. So we're going to see the interval to the left of here. So again, pick a test point. Doesn't matter what it is. You know, I just typically pick some whole number that is as close as possible, something convenient. So negative 4. So now we're going to substitute back into the derivative. So our derivative is not very pretty here. So we have to substitute it back into this. All right. So I'm just going to do the math. Okay, I'll be right back. All right, so it's positive. It's actually not as bad because this actually is always positive, right? Because of this being squared. So substituting it back into here. So it looks like on this side it's positive. So it looks like the function is increasing, okay, on this interval. So it's going to be increasing. It's going to hit a flat. Now my assumption is that it's going to decrease. It doesn't always have to do that, right? Because you can have something like this happening, where it is increasing, you know, increasing flat at a point, and then still increases. So don't always think that it goes from, you know, increasing to decreasing or vice versa. It can keep going. You know, there can be, okay, this type of activity which is happening. Now next, so what do we have? We have right here, okay, so on this interval, I guess I'm going to substitute negative 1. So that's much easier to do. So negative 1, so that's going to be 1 minus, well, 1 and plus 1, so this is going to be negative on top. So this is actually indeed is negative. So that means the function is decreasing here on this interval. And now on the next interval, so that's going to be right here. So what's happening? Well, I just blew that because I said this was negative 1. Well, negative 1 is actually over here. So I messed that up. So this is actually negative over here as well. Okay. Okay, so let's take a look. See, so this was, I just calculated this. I'm going to shift this over. So there you go. So you can see that's just my mind gap. But hopefully, you know, you get an opportunity to see. So I guess, you know, I could have chosen here negative 3, because that indeed would be between here and here. So let's just make sure that indeed it is decreasing. Negative 3 would be 9 minus 12 plus 1. Okay, I locked out. It is indeed still negative over a positive. So positive because this is positive. If you substitute back in, so this indeed is still decreasing. So it's going to look something like this. It looks like it's like this, hits a gap, and then blows up. Okay, so this is negative 2. And then over here, my guess, okay, so I guess it is, well, we'll see what happens. Let me see. So this is increasing, this is decreasing. Now it's decreasing here. Notice it's decreasing, so going from left to right. So that means over here it's going to look something like this. Probably, you know, hit a snag. Okay, so it's decreasing, and let's see what happens. I don't know if it's going to start to increase over here. Okay, so we have to check beyond this point. So, well, 0 is a nice point to check. On the right-hand side, so that's on the extreme right here. So if I plug in 0, 0, 0, that's positive. Yep. Okay, so that's positive on this side. So that means the function indeed is increasing. So it's going to look something like this, where this is your discontinuity at negative 2. Let's take out decimals, okay? And let's see if we were correct. Okay, so bringing decimals back. Let's hide this one away. What was this one called? H. Actually, it doesn't matter, but so hx equals All right, so putting it in, I'll put a bracket x squared minus 1 all over x plus 2. Yep, there we go. So it looks kind of like we had. And indeed, I guess it looks like, we can certainly graph this out as well, utilizing the tools from advanced functions, because this is a special case. Notice it's x squared minus 1 over x plus 2. So those ones we did graph before as well. I guess I'll put up a link up above there, those special cases. So we didn't necessarily maybe need our derivatives, but the derivatives do help us to confirm what's happening to the function, if it's increasing or decreasing. All right, so that would be it for this particular video. I think it's a nice concept to understand with regards to derivatives and how they help us to see where the functions are increasing and decreasing. Thanks for watching. All right, we'll see you in a future video. Happy studying for calculus. Bye, everybody.